right, in the foldable, you should be able to see on the tab of, let me see which tab would it be, on the tab of angles, measurements, let me see, measurements and classifying angles, you should be able to see some of these same definitions. See right here? So you have an acute angle is an angle that is less than 90, and a right angle is an angle that is exactly 90. And we tend to uh, use like a little square. So every time you see that little square, something like this, that implies that it's 90 degrees. Then we have the straight angle, which is equals to 180. And then we have the obtuse angle, which again, this is like an old foldable, so I don't even know if I put obtuse angle here. Um, it's an obtuse angle, see? So this is an obtuse angle, which you have it in here. So maybe you want to be able to add it to your angles because you have some angles in there, but you don't have obtuse. So you can say obtuse angle is greater than 90, but less than 180, because otherwise it will be a straight, right? And then you can have this as an example because this is an obtuse angle. So anything that you see, you can use your thumb and your index. Anything like this, see, that is an obtuse angle. This is a straight angle, right? But open it like that, and even something like this, right? Assuming there's a point here and then this is a here, that's also obtuse. Okay, this is acute. Acute is smaller than 90, see, and you cannot open it. You cannot open these two fingers to, at least I can't, to be able to be right? Ugh, kind of stretching it out there like this, but yeah. Okay. So obtuse greater than 90, less than 180. Straight is exactly 90. I mean, right angle is exactly 90. Straight is 180 because it's a straight line. And then acute is less than 90, but greater than 0. So those are the different, the basic different ones of classifying angles. But before we go into angles, angles are composed of um, different parts, right? They're composed of a point, a vertex, right? So all of that information, unfortunately, geometry has a lot of definitions. That is why usually I try to use a foldable, something fun that the students can do, and they can add information as needed. Okay, so so yeah, so there is in geometry. I don't know if you guys remember, right? But in geometry, we have not only a bunch of definitions that you have to remember, but we also use kind of those definitions to build on theorems and axioms, and then we start proving theorems. And as you prove theorems, then you can use them as proven. That's why I don't know if you guys ever did any truth, no, statement, proof statements tables back if you ever took geometry in high school. But they basically you all the theorems when you're using a specific book instead of label the whole name of the theorem, so it will be easier and faster to use them as proof. They will go by chapter. So let's say in chapter 1 you have 3 theorems, so it would say 1.1 for the first theorem, and then 1.2 for the second theorem, and then 1.3 for the third theorem. And once you prove those, then you can use them as proven and as true in chapter 2 and so on. So I have later on, I think one of the slides says axioms, what are axioms and what are theorems. But axioms is statements that are proven true. So there exists, the point exists. So if you see them and you can label them, so a point is 6. And points are labeled with capital letters, see? So point A and point B. Or you can literally write the word point A and point B. And yes, that A and B will be capital letters. Um, then it is proven that a line exists through any 2 points. So if you draw 2 points on a plane and you take your straight edge and you connect them, right, or go a line through them, then the line exists. Okay, so and lines are labeled in different ways. They can be labeled with the 2 points that you use to draw the line. They can be labeled with a lowercase letter, see, and that is called line B. I mean, sorry, this is line M. And they can literally name backwards or forwards. So, for example, this line, because again, you see that it keeps going to the left and keeps going to the right. So this line can be labeled line AB or line BA. Right. So, and then when you do that, because you're going to see that when we're labeling segments, we also do the same thing. We also use 2 points. Um, so the shortcut is that you are going to write the little arrow, see, like we did here on the top. So you that can distinguish the line, but still it's the same line. Okay. And then we have planes. Plane is just an area. Remember how we had Venn diagrams in 1350 and we had like universal set, right? That it was that rectangle. Um, so same thing. Plane is the area where things are happening. Okay, that's the plane where things are happening. And since this is 2D, so it's a 2D plane. And planes can be labeled either with a Greek letter, right? This is a Greek letter alpha, or they can be labeled with 3 non-collinear points. And you're going to have, I think you do, let me double check it here quickly. In basic geometric ideas. Yeah, in basic geometric ideas on tab, I think it's tab 6, you do have what is a point, the definition of a point, the definition of a line, an example of a line, definition of what is collinear. So collinear means that they are all in a line, right? That all the points lie on the line. And when I say non-collinear, basically I'm talking about that at least one of the points is not on the same line, okay? So for example, you see this is in your foldable. See, that's a point. This is a line that you can label it different ways. These 3 points, A, B, and C, are collinears. Why? Because they all lie in the same line. Now, for example, A, B, and C here are non-collinear. So AB may be collinear. You can draw a line here. Or AC is collinear. You can draw a line here. Or BC is collinear. You can draw a line here. But you cannot draw a line connecting all 3 of them. Okay, does that make sense? So that's why that when we are defining planes, you can define it with 3, right? With 3 non-collinear points. But you can also use a line and a point, not on the line, right? So you can use a line going through AB and then a point that doesn't go through AB. So again, there's different ways. In planes, if it's not using a Greek letter, we're going to use 3 points that lie on the plane. See, can be called plane ABC or plane BCA, CAB, ACB, BAC, CBA, you see? So you can call this plane anywhere you want. Now, segments, you are going to see, they're labeled, see, the same way as we do lines, but they don't have the little arrow. See the difference? See, and this one, we don't have the little arrow. So see, this one has AD and DA and has the little arrows. This one is AB and BA, but they don't have the little arrows. Why? Because it's a line segment, a piece of a line, where it has a beginning and an ending. And the beginning and the ending can be from either one of those endpoints. That's what we call that. These are endpoints. A and B are your endpoints. So we name segments by their endpoints. Now, when we go to rays, this is a ray. So what is the difference? The difference is that it has one of its ends, right? So this is not a line that continues on both directions. This is a line that continues only on one direction, and on the other direction, it ends on a point. And as a matter of fact, that point, that is going to be, the vertex for later on when we form angles, right? So we name rays can only be named in one way particularly. And I don't know here, this is so tiny, but this actually has a little arrow. Can you see it on your foldables? I don't know if you can see it. So basically this is AF and has a little arrow like that. Can you see? I don't know if you can see it on top of the thing, but so this is called AF, okay? You always going to label the rays by the endpoint first and then F, okay? So no, you cannot name it back and forth. So ray FA will be pointing, F will be your endpoint and will be pointing in the other direction. So you cannot do the same thing that we do with segments and we do with lines. Because it's to have a beginning point or an ending point, however you want to see it. Usually it's the beginning point and it keeps going on into one direction. Okay, so yeah, so that is the difference in there between rays, segments, lines, right, points, and planes. I am not going to ask you to define what is collinear, what is non-collinear, what is a plane. I am not going to do that, but I am going to ask you to label, for example. So you need to label the segment, or you need to label the line, or you need to label the ray, right, or the angle. So you need to be able to know how to do those things, not necessarily define them. I hope that makes sense. I don't think you have any of those as part of your vocabulary. So if you want to go to your vocabulary section, and then you should have a big space right there. I want you to go ahead and copy those 2 definitions, axioms and theorems. So axioms, again, is a statement that is considered to be true based on logic. Okay, so if you can see a point, it exists. If we can see you, you exist, right? This is not an existential thing like philosophy. Okay. So and it cannot be proven or demonstrated because it's simply considered self-evident. Okay. And then basically anything declared to be true and accepted, but does not have to have any proof or some practical way of proving it is called an axiom. Okay. And it has different names. It may also, you see it as postulate or an assumption. And we have those in in math, right? So not just in geometry, but in geometry is where you see it the most. And you have it also on some science classes as well. Okay. And we have then theorems, which is what you prove through whole geometry. And then on theorems, by definition, is a statement proven based on actions or other theorems that already have been proven true. Okay, and theorems often proven through rigorous mathematical and logical reasoning, and the process how it's approved will, of course, involve one or more actions and other statements which are already accepted true. Now you're gonna say, Miss Escobar, so I just want to teach elementary school. How the heck are we going to do all this? Well, not necessarily you're going to tell your student this is a theorem, this is an action, or we're going to do a statement, proof statement table. Not until they're older, right? But you saw in 1350, those of you that took it with me, right? You saw that we had to justify step by step with properties, right? So we were able to have a plus 2 equals to 2 plus 8 because of the commutative property of addition, right? So we proved that. So you kind of are setting it up. And yes, these are things that students in 4th and 5th grade can do because they should be able to be thinking in that way. Because we're trying to generate student thinkers since they are in pre-K. And part of the thing is always ask them why. Why do you say this? What are you basing your thinking? What are you using as basing your thinking, right? So in the best way they can. And sometimes they just can't do it with a drawing. And that's okay. We, as a matter of fact, one of the things we are proving, and you have in your homework, or maybe you don't have in your homework, but you do have it in your test. Maybe you do have it in your homework. Yes, you do. You do have it in your homework, and you have it in your test in the partial too, and you have it in the final. And that is proving the interior sums of a polygon. So we're going to do that by proving with a drawing. So as you see, it not may be a formal proof, like you would do in a formal geometry class, but it does start the thinking process of the student. Okay, and that's what we want. We want that thinking process to be developed. I'm sorry, I did not know if you guys finished this or not, but you can always take a picture and then just write both of them on your foldable. So this foldable not only is going to be useful for this chapter 3, but it's also going to be useful for chapter 4, for chapter 5, and for chapter 6. From now on, all we see is geometry. All of it is geometry. I apologize. I know geometry is not one of the favorite of most students because of this justification and thinking process and the ginormous amount of definition. But I promise that I'm trying to feed it to you little by little and trying to do activities that you will remember. Okay. So hopefully everybody took a picture and then they're writing it down. You don't need a summary because basically I kind of already told you all these things. And then again, these are things that I've proven they're already true. They're exactly one line that contains any two distant points. If 2 points lie in the plane, then the line containing the points lies in the plane. If 2 distant planes intersect, then their intersection is a line. And there is exactly one plane that contains any 3 distinct points. So again, this is something that maybe you can write on miscellaneous because not necessarily I'm going to ask you to write down these definitions, but I do have some true and false that you need to be able to know this information so you're able to justify your answers. I hope that makes sense. Yeah. So go ahead and take a picture. And again, these are actions. That means these things you do not need to prove. These are actions or postulates, whichever one you like. These 3 need to be proven. Okay? We are not going to prove it here because, again, I said this is something that you prove in a geometry class. So these theorems of point, lines, and planes. So a line and a point not on the line determines a plane. So we need to prove that. Not now, right? But in a geometry class. 2 parallel lines determine the plane. Okay. And 2 intersecting lines determines the plane. Because if they're intersecting, that means they have 1 point in common and other million points not in common. So obviously for determining a plane, you need 3 non-collinear points, right? And then you have it because you have 2 on one of the lines and 1 on the other line that is not the intersecting point. So as long as it's not the intersecting point, you're good. Same thing with parallel lines, right? So they're lines that don't intersect. So obviously you can choose 2 of the points on one line and 1 point of the second line, and those are your 3 non-collinear points, right? So there's different ways that we can do these right here. And then this is, like I said, you do have, like I said, the definition of a line under basic geometric ideas, right? And here I do give you even more information, right? Look at this line. This line can be named line L because you can use that little lowercase, oh, come on, a cursive lowercase L. And then, so we can say line L, or line AB, or line BA, or line AC, or line CA, or line BC, or line CB, because all of those points lie on the line, and you only need 2 points to name the line. And it doesn't matter, right? Because it goes back and forth. So it doesn't matter in which way. So see, this one line, you can name it in 1, 2, 3, 4, 5, 6, 7 different ways. Because that depends on the amount of information provided, right? I also give you a point not on the line, just because we want to talk about collinear and not collinear. So we can say that ABC are collinear because they're all part of the same line, but ABD are not collinear because D is not part of the same line. Okay, so you do have 2 of the points can be in the same, just the third one cannot be. When we talk about between in a number line, it literally needs to be in the number line. So we can say that B is between A and C, but we cannot say D is in between A and C, even though it lies in the same position, but it's not on the line. Okay. And then again, I already told you about line segment. I already told you about race. And then this is the next one. This is coplanar. So these are going to be points or lines that lie in the same plane. And you're going to say, Mr. Stewart, but isn't this pointing up? Yeah, that is trying to simulate 3D. Because remember, you only need 3 points to make a plane. Now, they say point D, E, and G, these bottom ones that form that blue thingy, they are coplanar. Yes, they're all both in this part of this plane. Points D, E, F, and G are not coplanar. Why? Because F is outside the plane. But lines D, F, D, E, this one right here. So can I, they will let me, let's see. So this one right here, that goes up, that one, that's a plane because you have 1, 2, 3 non-collinear points. So you can form a plane with that. So those lines are coplanar because they're part of the same plane that goes up. Okay, so DE and EG are coplanar. Again, they're intersecting lines, but D and G don't lie in the same line as E. And let me put there. And so yeah, so there's a different ways in here. It says D and EG are intersecting lines because they intersect in point E. See, that's what they have in common. And then this definition is also not in your let me see. Plane lines, semicircles, diameter, parallel lines, concurrent lines. So you have concurrent lines, you have this next one, but you don't have skew lines. So under basic geometric ideas, tab 6, go ahead and add skew lines. And you don't have to make the drawing that complicated, but you can just do the drawing. It says line DF, right? And lines GF, this one up here. And lines DE are skew lines, okay? So what does that mean? That means that, see, this is a line over here that is flat. But then you have another line, and think of, there's a space, right? So there's a space going up. So they are not going to be intersecting. The only way to show it, it will be like to do this 3D type of thing. Because in that way you understand that F is outside the bottom plane where DE lies, okay? So they are not intersecting. They are not intersecting, but they're not parallel, right? Because the only non-intersecting lines that most students know is parallel lines, right? So, but they have to be parallel, so they're going to be at the same distance, equidistance from each other, but not this one. These one, they simply don't intersect because they're in different planes. But you do have concurrent lines in there. And so you do have the next definition in your foldable. Concurrent lines, so you have DE, EG, and EF are concurrent lines. Why? Because they all get intersected at the same point E. And in the one in your foldable, I gave you like the 3 lines there. Line M, P, and N, M, and P, they're all intersect at point A. That is in your foldable for concurrent lines. So yeah. Okay, so hopefully you write the definition for skew lines. You have there in the same basic geometric ideas, you have parallel lines, the definition. This little symbol, which I did put it. This little symbol implies parallel. So it looks like a long L or double L's or long 11 or whatever, right? So that means parallel. So M is parallel to N. So that way you don't have to write the whole word parallel. But again, you do have that definition, these two, in your workbook. I mean, in your foldable. Okay, so these, not necessarily you need to know. It is there, but you don't need to know it. It says a line perpendicular to a plane that is perpendicular to every line in the plane through the intersection. Oops, what the heck? Oh yeah, this is the top. Sorry. And I say, why did I put planes first? There you go. This is the perpendicular lines, and you do have definitions for perpendicular lines. So you see the perpendicular line is always going to have either the 90-degree, right? Or it's going to have that little square. That is telling you that's perpendicular. And that upside down T, which you also have on your foldable also in basic geometric ideas, is the symbol for perpendicular. And you can have lines that are perpendicular, you can have segment that's perpendicular, you can have rays and segments that are perpendicular, and you can have two rays that are perpendicular, right? So you can have many things. You can have the lines, the two lines, two segment, two rays, a segment, and a ray, right? Or a segment and a line. Those are didn't put it, but you get the drift, right? So, and then we go to perpendicular planes, and it says so perpendicular planes, right, are going to be, see right here that this line, this is plane gamma, and this is plane beta, and they're both perpendicular, right? They form with this line. They are perpendicular for forming a 90-degree angle. Well, actually, the beta is forming a 90-degree angle down here with the plane alpha, which is the blue plane on the bottom. So this is perpendicular to that one, this plane to this plane, because of that right there. And then, but you really don't need it because I'm not going to, not right now. Like 3D shapes are not until chapter 5. So yeah, not right now. We will revisit whatever you need to know about the 3D shapes. Okay. Now, have planes, and again, I don't think I put it because again, it's not that important at the moment. But you can have a line and a plane be parallel to each other. You can have, obviously, the line is contained in plane alpha, and we can say here that the line L intersects the plane alpha in one point, and that point is P. So just think of, right? Think of taking your pencil through a piece of paper, right? So there you go. They intersect on one point. Then we have, of course, two planes that parallel and two planes they intersect. And when two planes intersect, the intersection, as you see, is a line. Think of the foldable that you just have with you, right? When you open it, don't you have one flipping over just like a book, right? So that line where the two are connected is a line, right? And then you have a plane on one side and the plane on the other side. Okay. And then these are perpendicular. So if P is any points A and AD, and Q is on plane alpha, and S is on plane beta, so that PQ, the ray PQ is perpendicular to ray PS, and PQ is perpendicular to AD. I don't know if you see this. AD is the line that both planes intersect. And this is that right angle right there is supposed to be like in the air, right? So just think of you holding the foldable in such a way that it looks 90-degree angle, right? So then we can say that that angle formed in the air is also going to be a right angle. But certain things need to happen. Again, I am not going to ask you to prove any of this. And not even to remember it yet, okay? More definitions. Let me see on angles. Measuring and classifying angles. Let's see. Yes, I did give you this information. And your foldable is like on the very, very top. First, it tells you an angle is formed by two rays that have the same endpoint. The common endpoint is called the vertex or vertices in plural. And again, that is like the first line that you probably not even see right after the title that says measuring and classifying angles part 1. And then after that, you actually have this kind of same drawing, right? This angles, and this is, I think I did, yes, I did put it. Angles can be labeled in different ways. Like you see here, you can use a number to represent the angle. So this is angle 1. And this is the little symbol of angle. When I was growing up, I was always taught to do this, just kind of to referring as an angle 1, okay? Or such. So if you see me doing the little curvy link, it's because that's how I was taught, and I still remember to this day. So this is angle 1, but you can also label, since the vertex is not shared with anybody. So take a look at in your foldable. Let me see right here. Take a look in your foldable. Let me see. I cannot call this angle angle B. Why? Because this angle, that vertex B, is shared by how many angles in here? How many angles can I form here? We
None?
have this angle.
Oh, three.
We have this angle. We have the big angle, right? So
Hmm.
we have three angles that share the same vertex. So as you see, I cannot name neither one of these, just angle B. But because this one is all by itself, I can just use the vertex. Now, what do you notice about these two that use three letters? Usually when angles are shared like this one, when the vertex are shared like this one, you must label the angles in with three letters, okay? And the vertex is always going to be, see the middle letter, you see right here? The vertex is always going to be the middle letter. So you can say that this is angle ABC or angle CBA, right? And in this case, because again, the angle is not shared, we can say angle B, or it's actually using numbers, so you can say angle 1. But in this one, you must use all three, especially when they are defining adjacent angles. Adjacent angles are angles that share a side. So that's what we call the rays that form the angles are called sides. So this is a side, and this is another side. And then this is your vertex right here. Okay. So we got side, vertex, and then the angle that is contained in the inside. So for these, here I can call angle ABD, that's that little one. And then angle CBD is the one with the two little lines. Oh, we also can use little lines like this one, see? To label the different lines, different angles. So these two angles measure differently because I use different things. And if you have a third one, let me actually use a third here and then a second one here. So I have the big angle, and that big angle is formed by this little angle, ABD, and this little angle, BDBC, right? And if you add those two, you form the big angle. And because those two share that ray, that side, we say that they are adjacent. Now, what can you not say? You cannot say that the big angle, ABC, is adjacent to ABD because they're overlapping. And that's why this says, so they cannot have anything in the inside. They cannot be overlapping. So adjacent angles cannot be overlapping. And you can write it down also. That's what it means. They do not intersect. It means that they do not overlap. See, I already did that. If you're going to measure physically with your hands, right, you can give students a protractor. This is a protractor. Protractor usually, the most common cells that they sell, they have little angles that you can use to measure from either direction. See, this one starts on 0 here and goes all the way to 180. But there are also, like I'm going to show you when I go into class. The ones that have in class, they have also interior. Then they're going to say we're going to go to 0, 10, 20, 30, 40, all the way to 90 is still 90. But this would be 100, right? All the way to 180. And the reason they do that, and then they usually have like a little hole or a little dot that's what you're going to put. This is what you're going to put on the vertex of the angle. Okay. And the cool thing of having those protractors that they're doable is that you can measure an angle either from the left or from the right. Okay. So I have here a righty and I have here a lefty. Okay. So if I were to use a protractor, I think this saved as an image, is it? Yeah. But anyway, so I will put it back. But see, if I wanted to do it, I will be placing that point right here and lining this bottom part with the side. And that means I'm going to start reading from the right, moving to the left. So I'm reading counterclockwise. So I'm going to be using these numbers on the top. And then, of course, you may extend, and this is at about, 45 degrees or so? But if you're using this one right here, then you want to be able to, and I cannot tilt it. Let me manipulate this instead. Okay. So you are going to, again, you're going to line up the vertex with the whole, then now you're going to be using those new ones that I wrote down, these. So this is your 0, and they're going to move in this way. But you're going to end with the same measurement, right? So in here. So this will be 10, 20. So if we extend this, it will go around here. So this is what, 10, 20, 30, 40. So that will be 40 degrees, right, for that angle. So it depends on the angle. Students, including yourselves, can only measure angles. Now, I don't know how many of you, by raising your hands, how many of you have seen these guys in the street, which are civil engineers that use this little kind of, they look like binoculars, but they're not binoculars because, well, maybe they are binoculars. They're kind of type of binoculars, but it's a special instrument that actually gives them to the second, um, to the second, specifically the measurement of an angle, right? We don't want our buildings to fall, right? We want secure buildings and we want it as accurate as possible, right? So, so same story. So they can measure in degrees, minutes, and seconds using those special instruments. The bare eye and using a little protractor is not going to give you minutes and seconds. But I did wanting you to know that just like hours have minutes and minutes have seconds, and then we even have what, microseconds. So when we're talking about hours, they're also similarly to angles. So angles are measures in degrees, and that's all you need to know for elementary school, right? Because you're not going to touch these until later on. But to be more precise, 1 degree is the same thing as 60. So here I have it as one of, but you're going to say that 1 degree is equal to 60 minutes. And we use that little apostrophe. Is that what they do it? And then 1 minute is equal to 60 seconds. Okay. Which means that 1 degree is equal to what? 60 times 60. So it will be what, 3,600 seconds, right? So yeah, so if you need a more precise measurement, then you're gonna need that little machine that gives you to the precise degree and seconds. Okay. And like I said, you would not work with these in your elementary school. But yeah, but if you are going into teaching high school, then yes, you are going to be able to manipulate this type of thing. And but it's the same thing. See right here. So you have the overlapping. One is the overlapping big angle, and two is the angle that you can measure from the floor. And again, most, or you should say all of our buildings are considered perpendicular to the ground. Okay. We are not the Tower of Pisa. That's not the goal. So we always going to assume that these angles are always right angles because they're always perpendicular to the ground. But anywho, so yeah, so you can measure this angle 2 measures the angle from the bottom of the ground to the top of the building. And then 1 measures from the bottom of the ground to the top of the flag. So you want to know how much the flag rises above the building, right? So to do that, to find this measurement, you need to subtract 1 minus 2, right? Makes sense. 1 minus 2. But 1 is given to you in degrees and minutes. And same thing is number 2. So what are you going to do? You are going to line them up like if they were place values, because they are. Oh, and then see, what else do you notice here? When you are actually writing the measurement, see, these are measurements. You put the little m in front. See how this one doesn't have a measurement? Because it doesn't tell you measurement. It's telling you what the name of the angle. This is telling you the measurement of the angle. So when you're talking about measurement, writing 90 degrees, 100 degrees, 20 degrees, 25 degrees, 40, then you're going to want to be able to write the little m in front of it. But anyways, that's just additional. So you would do what? 47 degrees and 45 minutes minus 29 degrees and 58 minutes, right? And then what do you notice right away? Can you take away the 58 from 45? No. So what are you going to borrow? You're going to borrow from the 47. So now you're going to have 46 degrees instead of 47. And that 1 degree, remember what did we say about 1 degree? 1 degree is equal to 60 minutes. So what are we going to be adding to 45? 60, not 1, 60. 60 minutes, not seconds. I'm sorry. There we go. So now I have 104 minutes. And I can subtract 104 minus 58, and we get what? Is it 47? Let me see. I have 47. Let me see. I need to do my little thingy. So we have 105 No, 104. Why did I put 104? It's 105. I'm going crazy today. Okay. 105 minus 58. And the funny thing is that I wrote it right on the calculator, but I wrote it wrong here. Okay, so 105 minus 58 is 47. And then 46 minus 29 is 17. And again, you guys are not telling me things. This is an apostrophe. There we go. So that means that that angle measures 17 degrees and 47 minutes. Okay. Now in this one, it says you want everything in degrees. So what are you going to do? You're going to convert, right? You're going to convert the minutes into degrees and the seconds into minutes. Now, I would suggest start with the smallest one first, right? We're not going to do anything with the 47 because 47 is 47. That's what we want. But we are going to write, let me just do 47 points. We're going to convert this to decimals that are in degrees. So first we're going to start with the 36. So we're going to do 36 seconds divided by 60 seconds is going to give you minutes. And that is 36 divided by 60. It's going to be 0.6. And then we're going to add that 0.6 to 45. So now you have 45.6 divided by 60, because these are minutes. And now you can have degrees. So we're going to add 45. And then we're going to divide it by 60. And that's going to be 0.76 degrees. So that's what you're coming right over here. And now the whole answer is in degrees, okay? Not just the 47. I hope that makes sense. So that's not what I wanted. Let me move on. So if you go to, yes, that one, that same one, basic measuring and classifying angles. So you're gonna see that you have an obtuse angle, that you have a straight angle, that you have an acute angle, and that you have a right angle. And yes, we realize that we don't have the obtuse in here. So for that one, you're going to write it, and you should have written it down already in your paper. And those are the same ones that you have on page 61 in your workbook, right? These right here. These are just definitions. But what fun way can you relate to angles with your students? So you can use a clock. So not only you help the students like work with the clock, reading clocks, but you can also help them with classifying angles, right? And that's a little fun thing to do. You can use what they call a, let me see, it has a weird name, but it's called a fastener. These little things, see, they have the open thing at the end. It's like a little pointy thing. They're called fasteners. I used to do this for rotational symmetry, but you most definitely can give your students a clock, and you can give them the arrow and the minute hands, and put it through a thing, and then they can form different ones, right? If you want something to open. I only have one thing because this was just for rotational symmetry. But yeah, but they sell these in Walmart or whatever, but they are called fasteners. It's a weird name for this thing. So at the same time, you also have a new vocabulary, which, let me see if I put it anywhere else. If you have central angle, because I know we talk about angles later on. Arc length. You do have the measurement of a center angle under polygons. Okay, but you can always write it if you want, because see, if you go to polygons, we are going to see later on, right, that we talk about central angle. But if you want to, because I only talk about the central angle, how to calculate the central angle, but you can always go to your angles, right, and then just write it. Mine, it will not read it because it's black construction paper, but you want to be able to add it here, somewhere in here, of what a central angle is, right? So the central angle, obviously, and you don't need to have just a circle. You can have a central angle with any polygon. We're going to see that later on. But in this case, since we have a clock, and this specific clock is round, so it is a circle. So we're going to use the center of the circle as your rotational part. And then we're going to have the rays, which is going to represent the hour hand and the minute hand. And those are going to be your sides of the angle, okay? And then whatever you open, that's going to be the angles for that, the measurement of the interior of those, okay? So, for example, in this one, like it says here, you see that a 3 o'clock arrow, it forms a 90-degree angle. See, that's a 90-degree angle. So, and that's what you need to do in this activity right here in part 3. You need to tell me the type of angle form. So we want to know this angle, we want to know this angle, we want to know this angle, and we want to know this angle. I don't want you to tell me what is the measurement, because I don't asking you for the measurement. I'm not asking you to use a protractor, but I'm asking you to classify as acute, obtuse, right, or straight. Okay. And for these, you also need to name also what appears to be acute, right, obtuse, or straight. So for example, I started the first one. So we're talking about CHF. So we're talking about this angle right here. That angle right there, that, see, if you want to put it like this, see, that's 90. So, and that still goes on. So that means that is greater than 90. So that means that is going to be obtuse. See, that's what you need to write down. So you need to write down the type of angle that it appears to be. On this one, I started it for you. I said that 1 is acute. This is 1. That 5 is right. So this means this is 90 degrees. And that 8 is obtuse. See, this right here is 8. And then you needed to classify all other ones, either acute, right, or obtuse. So, right, that should not be taking also a lot of time. And then on the bottom part of the clocks, I just give you the time. See, like I just told you before, 3 o'clock forms what? Forms a right angle, because we just had it as an example, right? But I would suggest just draw yourself a clock down here, right? And a generic clock. So this is 12, this is 6, this is 3, this is 9. And then you have 1, 2, 4, 5, 7, 8, 10, 11, right? And then again, have your students use their fingers or their pencils to find out the time. And no, because I did had somebody ask me this one time, believe it or not, I've been teaching for a long, long time. They asked me if it matters if it's 7 a.m. or 7 p.m. It does not matter if it's morning or night. It's still going to be pointing to the same location. And then I can write it, and that way everybody can see it. And that way we don't have to go back and forth between the screens.
Okay.
So 2 is
right.
2 is right. Uh-huh.
And then 3 is acute.
Okay.
And then 4 is acute.
Okay.
And 5 is straight.
There you go. Very good. They're all right. Okay. 6, Maida.
Number 6 is acute.
Okay.
Number 7 is acute. Number 8 is obtuse.
Okay.
Number 9 is straight. And number 10 is obtuse.
Okay. Perfect. Yep. That's it. See, this is obtuse. So look how big that is. Okay. Okay. So obviously, as you see, we must name all these angles with 3 letters, because see, they all share H. See, this would be one of those questions that they say, how many 7s do you see? Or how many dots do you see? Or how many eyes do you see? How many angles do you see? We got, yes, the obvious 1, 2, 3, 4, 5, 6. But then we have 7, 8, 9, 10, 11, right? And then we have what? We have 12, 13, 14, 15, 16, right? So depending on where you start and as you move along. And yes, there are angles more than 180, right? So if you start measuring here and goes all the way around here, that's going to be more than 180, because remember, a whole circumference is 360. So yes, there may be angles greater than 180. Okay. Part 2, Bobby. So which ones of these are acute besides 1?
Besides one, oh,
Yeah, I gave you 1 already. So besides 1, which are the other ones that are acute?
would it be 2,
2,
4?
4,
I'm trying to think. Would it be 9?
9. Yeah.
All right,
That's 1 more.
that's right. That's wrong. 3?
No, see, you can tell. This is 90, and that is even more than 90.
Yes.
So you know right away that's going to be what?
That's
Obtuse.
obtuse.
So 3 is obtuse.
Okay.
So they have to be less than 90. See, these
I'm
are
sorry. 7.
90.
7.
7 is not. 7 is right.
Oh, I'm looking at the wrong one. Okay.
7 is going to be right, and 12 is going to be right.
And then 6 and 5 is right.
6.
Well, 6.
6 also is right. Yeah, 6 is also right. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So what are we missing? 10, 11, and 12.
10, 11, 12. Isn't it?
So what? How do you classify 10?
So 10, 11, 12.
Look at the angle of 10. And again, you can always use your reference. Use your finger.
So 10 and
10 is what?
10 is going to be obtuse.
Obtuse. There we go. And then 11?
11 is going to be acute.
That's the one that you were missing in acute. And we got all the rights here. And we have all the obtuse here because we put 12 already. If 7 is right, 12 is going to be right because they form a straight angle. And if 5 is right, 6 is going to be right because it forms a straight angle, right?
Yes,
So,
ma'am.
and then we have all the other ones that are classified in there. Very good. Okay, and now we're going to do, we are going to do the part 3, part of the clock. So Victoria, so this is 8 o'clock, right? Everybody,
Yes.
everybody here knows how to read an analog clock? 6 o'clock, right? This is 8 o'clock. What does 8 o'clock angle is? This one right there.
Obtuse.
Obtuse. Okay. And then what about 2? 2 is what?
Straight.
Straight,
Hmm.
which is 6 o'clock. And then what about 3, which is, we're looking just at that tiny one. And what is that time?
4:30.
4:30. Very good. And
And this
4:30
is
is
acute.
acute. And then this is what, 2 o'clock?
Yeah, and that's acute as well.
And that's acute as well. Very good. And then Maida, so we already had the 3 o'clock was right? Because 3 o'clock will be like this. So that's a right angle right there. Okay. So what about 10:30?
10:30 is obtuse.
Obtuse. So right, we will put the little hand over here. It will be almost like halfway through, but like right here. And then it will be right here to the 6. And this is the angle that we're looking at. And that angle is obtuse. See, this will be an awesome thing of having students practice how to read a clock and at the same time look into central angles. And then that will be classifying angle. That kind of like knocks out of the park 2 things. But anyway, 5 will be what?
Acute.
Acute, because it's 1 o'clock. So this will be the little hand and this will be the big hand. And then there you go, the little hand is 1. So this is acute. Okay, let me erase all these. And then Bobby, what about 7?
Obtuse.
Right, so this will be 7, right? And I erase the vertices also, right? So that's 7. Yes, that's obtuse. And then this is 11:45.
Acute.
So 11:45 is almost 12. But it will be still that little one right there, right? So that will be acute. And then we have 9:05.
Obtuse.
So the little hands will go to the 9 and 05, right? We're talking about that big one, so that is obtuse. Awesome. Very good. Okay. Now, the next activity is what and I used to do this with my kids. I used to take originally these, I had pictures and I had strings attached to the flower pictures of my student. But the publisher told me since I did not have any release form, I couldn't, I could use it internally, but not publicly because I didn't have release from those students to use the pictures. But this is something that you could do like at the beginning of the year and then at the end of the year. And then, or actually give them the strings at the end of the year and they can see how much they have growth. Okay. So I used to do string, but not stretchy string, like a big string. And I used to measure them, how tall they were. And then they will stick that to the picture of them. And then we will put it on the wall and that will stay there. Like, that's kind of like, was like a beginning activity for my students, right? For the year. And then we will put it on the wall. I will tape it on the wall. It will be there all year. And then from there, right, at the very end of the year, I will take it apart and then give it to them. And they can see, they can find the difference of how tall they were at the beginning and then at the end of the year. But why is that? Why am I using strings? Or in this case, paper clips? Because one of the core things that you need to do in elementary school, and I think it starts on 1st grade, is to learn how to use non-standard or non-traditional measurements, okay? So, for example, a piece of string. I measured them as a piece of string. When we got to that measurement, that unit, we use I have used paper clips. I have used like an unsharpened pencil that I gave everybody, and everybody measured like the tables and the chairs and how tall they were in regards to pencil measurements. Okay. So yes, so you can measure. As a matter of fact, this is how the English system for measurement came about. They use like standard things. So for example, the traditional men's size shoe back in the day here in America, because America is the only one that uses the English system, which includes feet, inches, yards, right? Miles. Everywhere else in the world, they use the metric system because the metric system kind of goes along with our place value. Our metric system is based on base 10. So if you move from small to big, you divide by 10. If you go from big to small, you multiply by 10. And then there's like a system, like a units that you move about, right? But in our English system, there's no relationship. You need to know what they are, right? So that's what you see if you see in the next page, right? In the next page, you have the most common use metric, English, the most common use metric, and the bridges that we had to create so we were able to convert from one system to the other, okay? So inches. This is about an inch. Your thumb is about an inch, okay? So again, and then you are going to see that, like I said, the feet size of a common man back then, there was about 12 inches. So, and then we have, so that's what they call it. Oh, let's call it a foot. And then we have a yard. A yard, believe it or not, and my mom taught me this because this is the person. I'm trying to draw a person. So these are the shoulders and these are the arms. And I tried to draw a straight arm. I know it has more things than that, but it doesn't matter. Okay, don't criticize me. So my mom used to sew, right? So sew clothes, and she taught me that from the tip of the middle finger to the middle of your chest, this is about a yard. That is about a yard, like a normal. And she was actually 4'11". So it doesn't have to be. Obviously, we're not talking about a child, right? We're talking about a grown person. So the yard will be from the middle of your chest to about to the fingertip of your middle finger. And funny enough, this is your shoulder, the end of the shoulder. A meter stick. So we have yardsticks and we have meter stick. A meter is from the shoulder to the middle of your finger. So 1 meter is about 39 inches, and 1 yard is 36 inches. So yeah, so there's about a difference of 3 inches between the chest and your shoulder, right? So about more or less about that, right? So that's what I say approximately. So yeah, again, human measurements, right? So non-standards that we made as standards. So yeah, so we and then I know that there's something about the pace, like the pacing step that they use to find acres, right? We know we have acres, so they do like the pacing, and I don't remember right now the pacing, but that we have also acres, which I didn't put in here. That's how they use the width of the pace, right? How many feet were those, and then that's how we did conversion of acres. So as you see, we came from using non-standard measurements and we converted into measurements. So if you can do this at home, if you don't have the paperclip, because it's important that everybody has the same size paperclip. This is like a small, but now since they come actually micro size, I didn't even know they came micro until I saw them, but there's some micro size. But if you buy like the one generic type, right, that is a 3 centimeters, and this is like the big paperclip. We're not using this one, we're using that one. And I don't have any other micro. I used to have 2, so I used to show my students, but I don't have it. I don't have them anymore. Let me see. I think this is also the same. See, not even see. This is like the type that comes in those fancy things display that I bought for my daughter, and you see how it's not even the same size. So it has. That's what it's important that no matter what your non-standard measurement you want to use, you must make sure that all the students in your class are using the same one. That's what I gave them on sharpened pencils, all from the same box, and they were all the same size. And they were not allowed to use the eraser or anything from that on sharpened. They just needed to measure everything in that. Okay. So I can give you the paper clips because this is actually a picture of what I used to do with my students. See these right here? These are the paper clips. So you don't want to interlock it. I dumb enough did that one time. And then I had strings of paper clips that it took hours to undo. So I couldn't use it with my next class. So yeah, no. So what I do now is that I tell my students, trace your foot, and you can trace your foot in a piece of paper, cardboard, whatever. Trace your foot. You can trace it with your shoes on or without your shoes, be honest. And then you're going to take the paper clip once I give it to you in class. Don't do it at home. I will give you one paper clip, and then let's say this is my big toe right there. So I am going to measure. See, you're going to do this. You're going to measure Or if you have paper clips and you want to measure that it's actually 3 centimeters, let me see. I think I have a, see, these are centimeters. See, that's a 3 centimeter paper clip. So if you can measure the paper clip and make sure that you have a 3 centimeter paper clip, then you can do it at home. You can do everything at home. And you see that I don't have a whole piece right there. And this one I can say is what? I think it's more than half, right? I think it's like 2/3, 1/3, 2/3, right? So this is about 2/3, but this is one paper clip, another 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 paper clip. So you're going to say that your foot size is 1, 2, 3, 4, 5. Well, my foot size, 1, 2, 3, 4, 5, 6, 6 and 2/3 paper clips. And once you measure it, then that's what you're going to put in here. My foot is 2 and 2/3 paper clips. And then what the students do, because this is a cutout, right? So you will cut it out. And then I tell them, stand against the wall without shoes, put a piece of tape, because I do give them tape, put a piece of tape where you can reach, or have somebody else put a piece of tape in against the wall where your head, right, touches. And then from there, they measure themselves using their foot size and how many foot size they are. Now, what they need to understand, let's say they are 7 of these foot sizes, my size. Then you're going to put here, I am how many paper clips tall? Well, if you were 7 foot tall of your foot, right? 7, your foot tall. And you know that each paper clip is 6 and 2/3. And you can change 2/3 to 0.66 repeating, or 67. It's not writing. 667. And you're going to multiply those two, and that's what you're going to write over here. Because this is just telling you the number of paper clips for 1 foot, but you got 7 of those. So you will multiply those two, and that's going to give you a number of total paper clips. So let's say I did do that. Let me see. I got what? 6.67 times 7. So this is about 46.7 paper clips tall. And then we are going to use this measurement as an introduction to do conversions using a table. This is what it is. We are using a table conversion to convert the units. And then I have the units here that we're going to be using besides your paper clip tall. Okay. So where it says here, let me erase this. And this is just an activity that I wanted to do in class, but it was not possible. That's fine. So again, in this case, when I actually did do it with tracing my foot, that was just like an image. I think I used my daughter's foot. I had 8 paper clips in my foot, and I measured 4 full paper clips and 6 full foot and 4 paper clips. And you said, Miss Escobar, how do you know? Well, because if you measure yourself and then you stopped here, 1, 2, 3, 4, right? You were 6 of your full thing, but then you were only this amount left. Then you're not going to put a whole foot. You're going to put that as 1, 2, 3, 4 paper clips or whatever. Well, actually, this is 3.5. But so yeah, so you say I stop right here. So you're going to say, oh, that's 1, 2, 3, 4 paper clips. And that's what I wrote here. See? So I was 6 on my foot, which I'm going to multiply by 8 because that was the total number in that case that I had paper clips. And that gives me 48. And then I'm going to add the 4 paper clips in there. And that gave me a total of 52 paper clips, which is what I put in here. So what are we doing today? Because you do have a question in the test. And I'm sorry, my dog, see? This is what happens when I leave stuff on the floor. You would have a question like this on your partial exam and on your final. So it says, tell me, and even in the homework, I don't have the homework here with me, but I think it says, name, what are non-standard measurements? Okay. And name an example. So what do we do today? We use non-standard measurements to measure things. In this case, your height. But you don't have to do it if the height is too complicated for your kids. Just let them measure, do like a center. And on one table, you have a book. And another one, they have, I don't know, a piece of string that they have to measure. And another one, they're actually measuring the table, right? Or you have a bulletin board and you want them to measure. So or maybe you have a table that you want to measure the height of the table. So you can do several things that they have to do around the room. And they are with a tablet thing, right? With a little thing. And then they have to take measurements with their own foot size or whatever it is that you decide to use as a non-measurement model. Okay. And then from there, then you want to be able then to bring it back and says, okay, let's convert it to real size, right? So a real size, you're going to take whatever you had here, you're going to put it here. And as you see, I have these crossed out. Why? Because I want to go from paper clips units to real size foot units. Okay. So in the way, I have the one small paper clip is 3 centimeters. Since I want to go to feet, and feet is in the English system, so I need to have the bridge of the metric to English, because the paper clips are in metric. So I went ahead and I did 2.54 centimeters equal to 1 inch. So that's what I did here. I went ahead and I canceled one paper clip as 3 centimeters. See, that's the ratio that I use for this one. The units that I want is on the top. And then I don't want centimeters. I want to change it to inches now. So I'm going to put the 1 inch over 2.54 centimeters. So the centimeters cancel. And then over here, I have that 1 foot is equal to 12 inches. So, and I have inches here. So I need to put the inches on the bottom. So the key thing here is that to be able to have the units that you want, they need to be on the numerator or on the top at the end of your conversion table. And to be able to cancel them, you need to have the units, 1 unit on the top and 1 unit on the bottom. See? 1 unit on the top, 1 unit on the bottom, 1 unit on the top, 1 unit on the bottom. And then you're left with the unit that you want on the top. And then how are you going to do this? So everything that's in the top is like multiplying fractions. Anything that's in the top, you're going to multiply 52 times 3 times 1 times 1. And then you're going to divide by everything on the bottom. So you first multiply 12 times 2.5 times 1. And whatever you get, you're going to divide the number, the product on the top, divided by the product on the bottom. And in that case, this is going to give me the units all in feet. This is not saying 5 foot 12 inches. No, this is 5.12 feet. So if I want to know, because usually we measure it here in feet and inches, right? So I'm going to keep the 5. So 5 is my feet, but I'm going to take the 0.12 and I'm going to multiply it by 12 because I know there's 12 inches in 1 foot. And this is part of a foot, 0.12 of the foot. And I say that I will get around 2 inches. Of course, I am not 5 foot 2 inches. I am 5 feet 8 inches. There is always going to be human fallacy errors, right? When they're measuring, remember when we were talking about earlier in the previous chapter, that there's always going to be variability. And one of the variability is measuring. So of course, even though they're using exactly the same size pencil, when they measure things by human error, they may measure it differently. Okay. And that's okay, you know, but as long as they're not like completely 2 feet off, right? So that is something that probably they did wrong, right, in their calculations, and then maybe you want to revise and go over it with them. But if they're just a few inches off, hey, that's good. That's good. They were to the right side. So I don't know. I always found they had fun doing this. This were like and I did it with what, fourth graders, I think. So and they're kind of old already for fourth graders, but they still enjoy it. They still, you know, standing and moving around the room. They always love that. So and I'm measuring their stinky feet. Also, they also love that too. So so maybe you want to tell the parents so they be aware that the kid may come with stinky feet. We have linear measurements, and we're gonna have measurements that we use to for straight lines. We have measurements that we use for volume. That's a different one. So we have measurements that we use for weight. That's a different one, right? So we use pounds in the English system, while we use grams and kilograms in the metric system, right? To talk about weight. So yeah, so we have different. Then we have volume of liquid, right? So we got liters in the metric, and we got centimeters cube in the also as well in the metric for talking about volume. But we are going to see those other ones on the last chapter. So on the chapter, I think it's 5 and 6 or something like that. So then we're going to see more information about area and volume. Okay, so these again, the most common ones, the ones that I gave you in here. We do have that 1760 yards is the same thing as 1 mile. But again, you can always do the conversion with these 3. You also have, let's see here. See, you also have in here, see how does it work? And that's what I tried to put in your workbook. The detailed example that I put in there is this convert 0.50 miles to inches. So I went and worked through step by step. So you have starts on page 65 and continues on page 66, step by step, how to work and what to introduce until you get what you need. Okay. So again, the process to work a ratio. So I want to change 5.25 miles, which by the way, I want to point something out. MI means mile, and I think I did put it in your workbook. MI means miles. Which is used in the English system. And then we have M, that is for meters, which is used in the metric system. So there is a difference. MI is miles and plain M is meters, okay? And I did put some abbreviations also on your workbook on page 65. So you do have those in there. So in this one, we are changing miles and we want it in yards. So I'm going to put 5.25 miles. So whatever they give you, you're going to put it over 1. Or if you're just drawing a table, right? So I'm going to put 5.25 miles and then just draw like a long line and then just draw this right here. And this is over 1 because that's the original measurement. So yes, I know there is a direct conversion between yards and miles, but on purpose, I did it this way because I wanted to show you how to do the cancellation. Okay, so I have the ratio that, what do I want to say? That 1 mile was equal to 5,280 feet. So I'm going to put 1 mile on the bottom and then the 5,280 feet on the top. Why? Because I want to cancel the miles. I want to cancel the miles, so no more miles. And to cancel it, since I had it here on the top, I need to have it now on the bottom. So now my standing unit is feet, but I want to get to yards. So what do I know? I know that there are, 1 yard is the same thing as 3 feet. So I'm going to do, I have feet on the top, so I got to write that 3 feet on the bottom so I can cancel the units. And then I'm going to put 1 yard on the top. Okay. And now I can go ahead and cancel feet with feet. And now my standing unit is yard, which is what I wanted. And then what are you going to do? You're going to multiply 5.25 times 5,280. And let me do that quickly. 5.25 times 5,280. That gives you 27,720 divided by 1 times 1 times 3, which is 3. And remember, this is still yards. And once you divide 27,720 divided by 3, you get the 9,240. Okay. This is what you need to do on those problems on part 1 on page 66. You need to convert those units that I give you into the units that are left at the end. Okay. And then on part 2, I gave you the different ratios. So let me show you quickly because I want to be able to show you this so you can work this for next class. Where did you guys go? Okay, there you go. Share book. Okay, there you are. Okay. So you see right here? So let me show you in this one. So I want to go from feet to miles. So I already did the table for you. So this goes over 1. So I'm going to find conversion that goes from feet to miles. So I gave you that 1 mile, and this is in the previous page. The 1 mile is equal to 5,280 feet, right? So I'm going to come over here. And I'm going to write, since feet is on the top, I'm going to write feet on the bottom. That 5,280 feet is equal to 1 mile. Now I have the units that I want, miles and miles on top, and I can cancel feet with feet. So what am I going to do? I'm going to divide 6,600 divided by 5,280. And that's going to give me what? Let me use my calculator again. 6,600 divided by 5,280. So that is what, 1.25? So 1 and 2,500 miles is the same thing as 6,600 feet. See? So you need, in these ones, you need to create your ratios, and you may have to create more than one ratio, like the one that I show you here. I had to go from miles to feet and then from feet to inches. So I had to use 2 ratios for that. Okay. And that's what you're going to do on these. And then on here, I gave you different ratios, and you see here, the kilometers on the top and the 1,000 meters is on the bottom. This is on B. But in C, you have 1,000 meters on the top and the kilometers on the bottom. It's because they're different ratios. They're not the same ratio. See, 1 meter, 100 centimeters, 100 centimeters, 1 meter. Because you're not going to use the same one. Because if you need the centimeters on the top, then you use D. But if you need the centimeters on the bottom, then you use A. Does that make sense? So, and if you needed to use more than one conversion, this is on page 67. I already gave you the other conversions that you needed. See, here you needed one more conversion, so you just need to come up with one. Here you needed also one more conversion, so you just need to come up with one. Here you only need one conversion, see, because I did not give you anything else. And then on this one, you needed 2 additional conversions, and the third one that you're going to come up and write down here. Okay, see, so if you needed extras, I provided it for you, and then you just need to fill in the blank. So for example, take a look at 9. So we went from millimeters to kilometers. So I cancel the millimeters with this millimeters. Now I have centimeters on the top And here I have kilometers on the top. And here it has meters on the bottom. So I need to cancel centimeters. So I have to put centimeters on the top, on the bottom. So I can cancel it with this one. And I have meters on the bottom, so I need to put the meters on the top here. So you need a conversion that has meters on the top and centimeters on the bottom. So meters on the top, right here. Meters on the top and centimeters on the bottom. So I need A. So you're going to come here, you're going to put A in the box, and then you're going to put 1 on the top and 100 on the bottom. And now you're able to cancel the centimeters with the centimeters and the meters with the meters, and you're left with kilometers, which is what I wanted. So what are you going to do? You're going to divide 10,005 divided by 100 times 10 times 1,000. So basically you carry the decimal point 1, 2, 3, 4, 5, 6 times. 1, 2, 3, 4, 5, 6 times. So it's going to be 0.010005. See? Now in the test, they're not like this. In the test, they're going to be like these. That you have to come up with your own ratios. Okay? So and then what am I going to give you on the test? The same thing I gave you on the homework, which I think it was something like this. And I also gave you this acronym. King Henry died mainly drinking chocolate milk. And you're going to say, what the heck, Ms. Escobar? What is King Henry died mainly drinking chocolate milk? Well, because the K stands for kilo, hecta, deca, meter, which is the base one, deci, centi, milli. So I gave you this, see? King Henry died mainly drinking chocolate milk. And when you write it that way, this goes from big units to small units. So you may want to write what I wrote right here, okay? So if you're going from big unit to small units, you can just carry the decimal point to the right, the number of times that that units require. So let's say, and then if you're going from small, like from this end to that end, you are going to carry the decimal point to the left. And that's like the one we just did. So we went from millimeters to kilometers. So we needed to carry the decimal point 1, 2, 3, 4, 5, 6 times to the left, right? And the original number was 10005, right? See, and then if we carry it 6 times, it will be 1, 2, 3, 4, 5, 6. And then we add a 0 in any empty space. See, we get the same thing. So I know what's the next question. Ms. Escobar, do I have to do it with a table? If I ask you to do it with the table, yes. On the activities, I ask you to do it with the table. On the homework, I think I asked you to do it with the table too. Okay, because I gave you the table and you need to draw it. So I gave you the table. So you need to, I think it's the first one, right, on the homework. So you need to be able to draw that table and do it with the table. But this is the reason why the metric system is so used, because you don't need a table to be able to convert from big units to small units. You just need to carry the decimal point, right? Just like we will do with place value, because we go right from big to small when we're dividing by 10 or multiplying by 10. So yeah, but this is what the prefix stands for. Kilo, hecto, deca, the base, because we're going to see this same prefix, but with liters. Okay. And we're going to see, hold on. Oh no, Adam is too early. I am not going to answer that. And then we have, and then we're going to see with grams. So instead of being meters, it's going to be kiloliters or milliliters or kilograms or milligrams, depending on what unit of weight or we had, right? Or the weight in liquid or the weight in how much people weight, right? So weight that time. So yeah, so I am not going to give you this. I am going to give you these acronyms. CHD, MD, CM. That's what I'm going to give you on the test, okay? And on the homework that you have. Let me see. The other thing, I wanted to see right here, 1 meter goes from the shoulder to the fingertip. That's a meter. Decimeter, it will be used for the width. Because also one of the things in the STAR test that students need to associate what units are more likely to be used to measure things, right? So if they say you're going to measure a car, the smallest cars are around like what, 6 feet, 7 feet long, right? The smallest car possible. you're not going to tell them that you're going to measure it in millimeters, right? What will be a more appropriate measures to measure? Meters, right? So we can measure in meters. How meters long is your car? If you're talking about the height of a person, right? So that's what they use, centimeters for the height of a person. So yeah, so we use both. We use feet and inches to measure, not just one. So yeah, so it is possible. Okay, so this is the next activity, and I am going to, so you can actually download it or use it, I don't care, in your phones or in your computers, since you're in the computers. Let me see, do I have the link here? Yeah, this is the right link, I think. Let me check it. Oh my goodness, one. There we go. So take a picture, because I do want you to, we're going to be using this to work with triangle inequalities. So make sure that you open it on your phone, and so in that way you can use it on your phone while we are in class. But yeah, so this website, we're going to be using it to find out what are possible sizes of triangles and what are not. Okay, so for example, I am going to where's my Zoom? Right, that first activity, oh, that's not it. There we go. That first activity is asking you to use string. You don't have to use string, but you may want to go ahead and use a ruler and your pencil and draw whatever you see on the screen here. So this says, I give you on page 68, I give you what is considered an acceptable triangle. That means that vertex of one segment lie on top of the vertex of another segment, okay? And there is no gap. There is not overlapping. They have to be right one on top of each other, right? So it's a closed figure, and they don't overlap, and they close, right? So, and then I gave you two that are not acceptable, right? That was in your workbook. So this is how you use this app. So you can make this bigger or smaller. That's the one thing I like also. And then we can change the sizes. We can change the sizes of the length of the segments for whatever you want. So for example, on A, it says, can the segments 5, 6, and 7 be parts of a triangle? So I'm going to make the blue one on the bottom 7. And you can make any other one 7. Then I'm going to make the green one 6. And I'm going to make the red one 5. And then, you see right here, I can move the thing. But don't trust it. I want you can just drag. See, get and drag, and then roll up with the finger. I want you to make it as big as possible, because you need to see exactly in where point. You see right here? And I like this because this gives you intersecting circles. See? That is exactly lying on top of each other. Let me see, where did it go? See, it's even, they still have a little bit discrepancy. I can still move it right on top. See? And if we kind of zoom out, like do the rolling thing out, I don't know how many times I did this to make it so big. Anyway, see, we do have a closed figure which has a triangle. So we can say, so what you're going to do, and depending on how you draw it, you can have any other size be 7 and the other one 5 and the other one 6, and the triangle may look different, and that's okay. Okay. So, and that's what I want. I want you to draw the different triangles that you can make, right, with this. So if I decided to make the 6 into a 5, and or decide, let's do this. Let's decide to make the 5 into the 7, and the 7 into the 6. See, we have another different type of triangle. And that doesn't mean that they're wrong. No, they're right. It's just they have different angles. The angle changes, but the size remain the same, right? So you can create different triangles, and that's what I want you to do on part A. I want you to use the app, because it's easier. Use the app, and then draw a couple of triangles there. And then do the same thing with part B. On part B, you need to use 3, 4, and 9. And then use it and try to figure it out if it's going to form a triangle or not. And then on page 69, you got a bunch. You got 2, 4, 6, 8 of them. So you need to test all of those. And then let me tell you something. I am going to show you right away here. So I'm going to say that this is 2. No, this is 2, and this is 4. Okay. And you can say, oh, it touches, Ms. Escobar. Do they really touch? Like really on top of each other? They don't. See, the bigger you do it, the bigger you make it, you can see that they don't, okay? They don't go on top of each other. And even here, they still don't go on top of each other. Even though it's really close, see? They still don't go on top of each other. Right? So this should give you already a hint right there. Oh my God, I don't know how many times I make it big. Hold on, there we go. How many times I made it big. But look at this. 2 plus 4 is 6. And you see that they look like they go on top of each other, but they don't, okay? So have that in mind, because that's what we're going to come with, a relationship between the sum of any two sides with the third side. And we're going to come up with a definition, because that definition, you are going to, I think you have to write it on the homework, but you also have to write it on the test too, and you also have to write it on the final. So you don't have to write all that. And remember, this whole chapter is not coming on the partial 1. It's coming on partial 2 and the final. Partial 1 only works for chapter 1 and 2. On page 65, 66, and 67. Exactly like that, which means you need to draw a table, and you need to draw the ratios, and you need to be able to do as such. So for example, let's say that the only thing I'm going to give you also when you do partial 2, I also going to give you, if you need any special ratios for the English system, I will put them in there. And then for the metric system, this is all you're going to have. And if you read the notes, you're going to see that I have an acronym to remember the order of the metric system. So basically the kilometers, or the kilo, right? So this is King Henry died mainly drinking chocolate milk. You can create whatever mnemonic you want, it's fine. But basically it's kilo, hecto, deca, meter, right? And then deci, centi, milli. And the cool thing about the decimal system, the metric system, is it works in base of tens. So these are the bigs and those are the small. So if you go from big to small, you're multiplying by 10. If you're going from small to big, you're dividing by 10, okay? But how would you work this out? So let me show you. Let me go here and do one. So for example, on this one, that you're going from inches to miles, right? From inches to miles, you're going to put this number here. And I'm just going to use this one so I don't have to write, because I'm writing with the mouse and it's really bad. So you're going to do that. Whatever number I'm giving you goes on the top. The point of these tables, which are ratios, is to cancel the units that you don't need. Right now, I'm giving you units in inches and you need miles, but I don't have a direct conversions of inches and miles. So what do I have? I have the 12 inches at 1 foot. So since I need to cancel the inches and the inches are on the top, I'm going to write the 12 inches on the bottom. And then the 1 foot on the top. Why? Because this allows me to cancel the units of inches. Now you're left with feet, but you don't want feet, you want miles. But you do have a conversion of feet and miles. So since I need to cancel the feet and the feet is on the top, I'm going to write this feet on the bottom. So you're going to have 5,280 feet on the bottom and 1 mile on the top. And by the way, I don't know if you see it in the class notes, MI stands for miles, M stands for meters, okay? And then I can cancel this foot unit with this foot unit. Now what I have left? Oh, I'm left with miles. That's exactly what I wanted, see? And now what do you need to do? You need to take this big number and you need to divide it by 12 and you need to divide it by 5,280, right? So, because you will multiply everything on the top and then divide it by everything on the bottom, right? So if you do 5,000, let me see right here. Can I pull a calculator? So I'm going to do, let me just do this one. Okay. I'm going to do 538,560 divided by 12 first. And I get 44,880. And then I'm going to divide that by 5,280. And you're going to get 8.5. So your answer here, I'm sorry, I was using the calculator to do it. The answer here will be 8.5 miles. But if you don't show me this work, just like I show you, you do not get credit. So if you only write 8.5, you get a 0 for that, but you're not showing your work. Remember, you are going to be future teachers. So you're not going to stand in front of the class and says, okay, the answer is 5. But miss, how do you get 5? Or mister, how do you get 5? Well, if you don't show the work, how are they going to know? Okay. So yes, it's important. And not only that, showing your work shows you as a teacher or me as a teacher, if you are making mistakes when dividing, when multiplying, if you understand the cancellation of units, so the converting of units. So again, that helps see what the students is struggling with. So there you go. I gave you 2.5 points already for free. Okay. Now let's go to in this one. So if you go through the chapter 11 class notes, right, you are going to see that we talk about a simple polygon. So the definition of a simple curve. A simple curve is just a curve that doesn't cross itself. Okay. So for example, this crosses itself. That's not a simple curve. Okay. So you need to select from here, and you have one problem very similar to this one on the test. Okay. So what is a closed curve? A closed curve is where the starting and ending ends at the same place, right? So that's a closed curve. This is not a closed curve, right? Because it's not even closed. It doesn't have, it's open. Then we got a simple closed curve. So what does that mean? That means that it cannot cross itself, because otherwise it would not be simple. And it's actually closed. It starts and ends where it started. And we call it closed curves because they can have curves, right? These three have curves. But we can also refer this to curve, but this is a special type of curve because this is made of straight lines. So then we have a polygon, and a polygon is made of, poly means many angles, basically polygon. Now, to be able to have an angle, you need to have the sides needs to be straight. So that means they're made of segments. So a curve that is made of segments is called a polygon. And a polygon is a simple closed curve. Now, as you see, there's two types of polygon. We have the convex and we have a concave. Okay, so the convex is the one where all the pointy parts are pointing out. The concave is whatever is pointing inwards. And a definition that you have in your foldable, if you ever did the foldable for this chapter, is on the very end of the chapter. If you did the foldable, it will also say that if you draw any line segment or that contains one dot inside the polygon, or both dots are inside the polygon, but when you draw the segment connecting them, it actually crosses outside, like part of the segment is outside, then it is a concave polygon. Okay, so I think I cannot tell you anymore, because otherwise I will be doing the matching myself. Then on number three is exactly as problems from chapter 68, page 68 and 69. They're exactly that. And you should be able to have so whatever you answer for part 2C on the bottom, then that will be what you need to explain the answers. To show your work and explain your answer, that's what you needed to do here. And you can actually, to do number 3, you can actually use, let me go ahead and show you. We are going to go to GeoGebra. Yeah, Triangular Maker. Like on page 69B, it says it's 20, 10, and 7. So you can do, see, you can just with a mouse, you can make it smaller. So we're going to do 20, 10, and then 7. And the thing is, let me see, I think you could, I'm going to move it out of the way. So I'm going to put it over here. And we want this to be 10. Let's move this further, 7. And this one was 20. Right, and then you need to figure it out. Now, do you have to make the 20 in blue? No, you can make the 20 the green one or the red one or whatever. But what do you notice? Can I make a triangle? Can I? No, right? No, I cannot make a triangle. So, and then when you go through the process, let me show you another one. So let's do 15, 12, and 9. So I'm gonna do 15, 12, and 9. And then yes, you're gonna have to play with this, see? And when you're doing this, you need to be very careful. You can do this, make it bigger, so you can actually see the intersections. See? And the bigger you make it, the better you can see if they're actually intersecting, see or no? There you go. And now you can close it. I would just put it down. I did it so big that, okay, there we go. So I'm zoom in. So you see that this one, yes, you can form a triangle. So then the next thing for you to do is to compare what's happening, right? What is the difference between the previous one and this one now that you, why this is not making it. The things that tells you on that page 69 is, can you find a relationship between the sum of any two sides of a triangle and the third side? Okay, so we know that this one works. So we are going to go and add any two sides and compare it to the third side. Any two sides and compare it to the third side. Any two sides and compare it to the third side. And then what do we notice? We notice, gosh, it's not working. Okay, my computer doesn't want me. Let's see. I'm saying it doesn't let me. Okay, whatever. So what do we notice? We notice that when we have, nope. Why don't you want to? Let me do this again. Do share again. I think this tends to happen when I have when I just had another class and it just changes everything. Let me see, annotate. Okay. So what do we notice? The 9 plus 12 compared to 15 is greater than, right? Because this is what, 21? So 21 is greater than 15, okay? Then we're gonna look that 9 plus 15, right? Compared to 12, it is going to be also greater than 12, right? Because this is what? This is 24. And then when we compared 12 and 15, of course, that's going to be greater than 9, right? That's 27, right? So when you see that the sum of any of two of the sides adds up to be greater than the third side, it works as a triangle. And look at the one that didn't work. The one that didn't work was 20, 10, and 7, right? So if we have 20, 10, and 7 that we see clearly it didn't work, right? As we draw it. So you're going to see that you have 20 plus 10 compared to 7. Yes, that's bigger. Okay, because this is 30. When we do okay, when we do 20 plus 7, of course that is going to be compared to 10, that's also going to be greater than 10 because this is 27. But what happens when you add the two smallest one? When you add 7 plus 10, what do you notice? The 7 plus 10 is actually less than 20, right? Because it's 17. And you see when one of them is less than and not greater than the sum, it doesn't form a triangle. And that's exactly what you need to, write on that number. What number was it? Let me go back here. Hold on. Where did I put it? Yeah, on this one, on number 3. Okay. On 3A. Okay. Let me actually go back and clear this out. Let me do clear. So the work that I just did for this example, that's the work that you need to do for your problem right here, okay? For your problem. So you show your work of all 3 sides and you add it up, 2 of the sides and compare with the third. And then you're going to say, yes, it is a triangle, or no, it's not a triangle, because the sum of any 2 sides of the triangle is going to be greater than the third side. And it says greater, not greater or equal. So equals don't work, okay? And like I said here, it's not only tell me the difference, but also give an example for each one, okay? What is an example of a standard measurement and what is an example of non-standard measurement? So not only the unit of measurement that you're using, like if you're using a ruler or you're using a pencil or whatever, or a paper clip, it's just give me an example. And then on this one, this is reflectional symmetry, which actually is part of the activities that you have on page 71 in your workbook. Like I said, if you go through the activities in your workbook, this is how I build the homework, okay? So and then also the class notes, obviously, because that will give you the feedback. So in here, symmetry means that they lie on top of each other, okay? So they lie on top of each other. And so if you cut, let me see if I can put here, annotate. And I think I can only write. I don't have lines in here. So you can say, okay, well, I can cut this figure in half. And then you to tell me, if you fold it through there, right? If you fold this through that line that you just draw, would all the things lie on top of the other side? If the answer is yes, then that will be one line of symmetry. So you need to find all possible lines of symmetry, not just going through this one vertex. And what if I do it this way? What if I do it that way? So you need to find all the lines of symmetry and label it. Line 1, line 2, line 3, line 4, right? And label it. Then the rotational symmetry, let me do clear here. The rotational symmetry is on the next page. It's on page 72. And the rotational symmetry says, if I find the center, because to have rotational symmetry, you need to have a center. So if I can find the center of the figure, and then I can go ahead and let's say I'm going to look only at this little piece. Can I rotate this little piece? How many times can I rotate and still get the same figure as the original? So if you can rotate it 20 times, then you put rotation 20 times. And then since you know that a full rotation is 360 degrees, and you can rotate it 20 times, I'm exaggerating, that is not 20 times, then you can say that this is that the rotation goes by what? So this is cut in half of 36 is 18. So that means that you can rotate in powers of 18. So 18 will be the first one, and then 18 times 2 will be the second one, and then 18 times 3 will be the third one, and so on until you end back to 360. So you need to write all the angles of rotation, right, to be until you get to the original. And that is what we call the what do I want to say? The order, right? So in this case, since I can rotate it 20 times, so the order is 20, and then you should have 20 angles to show. Obviously, once again, that is not this figure. It's just an example. So, and then, so you need to, for both, you need to tell me both. If it has line reflection and draw them, and if it has rotational symmetry, and also tell me the angles of rotation and the degree. And then part B has nothing to do with A. It's still symmetry, but it's not referring to the figure of A, because it says which of the following has exactly 3 axes of symmetry. So you need to draw these, and then which one has only, right? Because it says exactly only 3 axes of symmetry. It cannot have more than 3, only 3, right? And then you select the multiple choice, but you also need to show me. Let me just cut this one out. There we go. This one, number 5, this is coming on the partial 2. This is coming on the final exam. And this is also in your workbook, and it came in the homework. So if you go to page 74, the step-by-step instruction that you need to explain are right there. They're right there. Let me show you. Using the picture proof method. That's an octagon. And these are the steps. So you must write these steps, step 1 and step 2, not only on the homework, but you also need to write it on the test. Okay. And then you need to apply what the rule says, the step says, apply it to this. So for example, in this one, I'm going to show you with this one. In this one, which are also in the class notes as well. I do have the pentagon in the class notes, and I demonstrated in the class notes. But in this one, right, it says select a vertex. I'm going to select vertex A. Draw all the diagonals from that vertex to the non-adjacent vertices. So this is adjacent to A, and this is adjacent to B, to A. So I'm going to do here, this is 1, and this is 2. Then count the number of triangles forms. I got 1, 2, 3 forms. And then what do we know? We know that the sum of the interior angles of a triangle is 180. So that means I have 180 here, 180 here, 180 here. So you need to add these 3 180s, so multiply 3 times 180 to get the sum of all the interior angles or the pentagon. And if you do that, you will get what? 3, let's see, 3, this is 360, and 360 plus 180 is 540, all right? So that means that the sum of the interior is 540. Okay? So, and that's what I did in here. So, because it says find the sum, okay? Not the individual, the sum. So, and that's exactly what you need to do on that problem on your homework. And let me go back to the homework. Where did it go? Share. And then from the activity that you have on page on page 75, that you are exploring the number of you're exploring the sum of the interior angles of regular polygons. And I ask you to tell me what is the sum of the interior. And then in this case, I tell you a dodecagon. You need to know what a dodecagon is, how many sides this dodecagon has, and then show me the work, because there is a formula to find, which you actually go through the activity, you will find the formula, okay, for finding the sum of the interior angles of a regular polygon. And then that's what you do here. You use the formula for this part. So you explain on the first one with the proof, picture proof, but with this one, you just apply the formula, okay? And then on this one, again, it's all about understanding the properties of quadrilaterals and triangles and circles and polygons. right? This is where the foldable and all that vocabulary comes handy. And the thing is that for the false, you can just only say false. You need to tell me why it's false, okay? So for example, a square comes from, think of the parents of the square. The parents of the square, it will be the rectangle that gives the square all the right angles. And it comes from the rhombus, and the rhombus gives the square all the sides equal. That's why the square has all the sides equal and all the angles are 90 degrees. And I just answered the first one for you, right? So you just need to be able to know all those properties. And all those properties, I think, are part of, in the notes, are on 11.3. That's what I put all the properties for quadrilaterals and triangles. And you can go from there, okay? That's what I say about diagonals. Everything that is in here is on your class notes, okay? Now, supplementary and complementary. So the definition, you even have some definitions on page 77. And you have both of them. Complementary angles are angles that add up to 90. Supplementary angles are angles that add to 180. Now, if they say that the ratio is 2 to 3, right? So let me do a similar example, but not the same. So let's say that I tell you that one ratio is 1 to 9. Let's say that's my ratio, 1 to 9. And I want to find the supplementary angles. That these two angles are supplementary. What does that mean? That means that when I multiply 1 times something and add it to the 9 and the same something, that's going to give me 180. So in other words, that's something you can replace it with x, right? And then just work it out like if it was a simple equation. You're adding like terms, and then you're solving for x, okay? So, and that is for supplementary. And then once you find it, then whatever you get for x, right? You're going to multiply by 2, and that gives you the smaller angle. And whatever you get for x, you're going to multiply by 3, and that's going to give you the larger angle. And for complementary, they add up to 90 and not 180. So this now adds up to 90. And it's the same process. You're going to add like term and solve for x, and that's going to give you a value for the x. And then you're going to come here, and the smallest one, you multiply by 2 in your case on your homework. And the bigger one, you multiply by 3 in your homework, right? Okay. For 8, again, we keep going on. 8 is exactly like the ones you have on page 79. In the page 79, you need to explain why. Now, when you say, Ms. Escobar, what the heck is explain? And what do you need to explain? So, for example, 115, and I'm giving you this one already. 115 and the letter Z are vertical angles. And what do we know about vertical angles according to definitions? So let me actually write. Let me go here for a second. Let me do share the workbook. Okay, so let me make this a little bigger. This is, again, page 77. So I'm going to write a few annotations in here. Vertical angles, yes, they're opposite by the vertex, but they're also are congruent. So if I tell you that A is 100, then B is also 100. Okay. And then if I tell you corresponding angles, I did write it down in here, corresponding angles. Corresponding angle, that means they are in the same position, see? Corresponding angles are congruent. Alternate interior angles are congruent. Alternate exterior angles are congruent. Consecutive interiors, you can also have consecutive exteriors, but consecutive interiors or same side interiors are supplementary. So they add up to 180. Not the same, so they add up to 180. So corresponding, and they correspond to the same position. See, this one's just on the top right corner. This is on the top right corner, but on a different street. Okay. Alternate is because they're alternate in the transversal. This one is on the left side. This one is on the right side. This is on the top left. This is on the bottom right. Alternate interiors, and we have the same thing with alternate exteriors. Top right, bottom left, right? Alternate exteriors. And the same side is because they lie on the same side, see? And they are consecutive because they're one after the other. So those are supplementary. Okay, so the only thing that you need to add is that vertical angles are congruent, okay? So on the problem, I want to see if I can see here. If I have, right? So on this one, you see how I have, I can work this one with you. So you see in this one, first I noticed that 115 and y are alternate exterior. So you're gonna put here that y is equal to 115 because they're alternate interior angles and they are congruent. So that means this is 115 also. Then to find x, what do I notice? I know that 5x plus 5x is going to be equal to 115 because of two different things. You can say that they're corresponding because they correspond to the same position, top left, right? And then you can say that. So, and then we solve for x. That's 2, 10, 15, 3. So you're going to say that it's 23 and it's just x. And then you're going to say that is because they're corresponding. Corresponding angles are congruent. Because Miss Escobar, what if I notice these two are vertical? Then you can say vertical angles are congruent. So yes, so there is not just one right answer. It depends, whichever one you see first, okay? The same thing you have in your homework, right? Same thing. So we go on the homework. Let me go back to the homework. Right, same thing here. When I say explanation, you need to tell me that. Are the vertical angles congruent? Are there corresponding angles? Are there same side interior? Are there supplementary? So you need to tell me that. And the same thing here. Remember, 90 is a straight angle, right? So, 90 is a right angle. But if you look into here, let me get a notation, right? What does that 90 and this blank add up to? Like, what do they look? They are a straight angle, which is 180. So if this is 90, that means this is also 90, which means this is also another straight angle, which is also 90. And you can tell these were vertical angles, right? So again, you may have to do other things before you go answering the question. And then on 10, these are scenarios and you need to explain why or why not. Okay. So you need to look at can a triangle have two right angles? Why or why not? And you need to explain with mathematical knowledge. Okay. So, and I can help you with that one. So this will give you an idea to answer the rest. So can a triangle have two right angles? What do you guys say? Yes or no? Why? Because what do we know about triangles? That the sum of the interior angles of a triangle equals to 180. You literally need to type that in. Okay. You literally need to type it in. And then you have in there, right? So if you have two right angles, that right there is already 180. What's happened to the third one? There's no third one. So it doesn't work. Okay. So you're going to say no, because the sum of the interior angles of a triangle adds up to 180, and 90 plus 90 is 180 already. What happened to the third side? What would the third side be? 0, then it would not be a triangle. Does that make sense? So that's what you need to do for A, B, C, and E. Okay. That's what exactly you need to do. You need to prove it. And if it's yes, you tell me why yes. And if it's no, then you tell me why not. But they all need to be answered with a why or why not. Okay. Does that make sense? So